In this video, I'd like to cover a little bit about the perspective projection matrix. Normally, we got this orthographic projection, creating an X, Y, and Z, which I kind of explained in the previous tutorials. What we need to do now is we need to get the positions that they're perspective correct. So we got to scale them based on their depth towards the center of our view. So for example, if you imagine we're looking at this from top view, and this is our camera or eye position. This is our far clipping plane, and the geometry on the right side of that plane will be clipped by the hardware. And we'll have a near clipping plane, which I could show right here. And anything behind this will also get clipped. And the width of this near clipping plane is kind of determined by this field of view. So what our field of view is this angle here, and that's, you've probably seen in a lot of games, so you can adjust the field of view. That's how wide you can see things. So the wider the field of view, the more things you can see, obviously. And you probably remember that the tangent of an angle is equal to opposite over adjacent on a triangle. So if we need to know one of these lengths, we can use the tangent of the field of view divided by 2 for one of these triangles. So if you work out that equation, we got the opposite is this distance d here, or I should say we got the adjacent. The adjacent is this distance d here. And if we want to know the opposite, this length here, we can get that from d times tangent of field of view divided by 2. So whatever this angle is here, and that'll give us this length here, which is what we're after. So that's the size of the near clipping plane. When we project coordinates, what you may notice is that if I have, say, some object here, some panel, and if I take this point and figure out where it intersects with our screen here and here, what we just did here is we projected these coordinates onto where it would be in our two-dimensional screen that we'll display. And I can show you that that works, because if we move this back to, say, here, and it's the same size, it'll scale down based on distance. So if I draw a line from here to here and here to here, you'll notice that because it's further away, it'll be scaled a little closer to the center of the screen. So when it's close, it'll be bigger, and when it's far, it'll be farther as expected. And you can kind of see that from this. So for example, if I have this square here and I want to figure out where this coordinate should be projected to in our two-dimensional display, what I can do is draw a line from here to here. We'll just imagine that this line actually goes to here, and this one's perpendicular to here. So we got two similar triangles here that are perpendicular, so their length ratios will be the same. So all we have to do is we have this value here, which is x, because we're looking at it from the top view. It would be the same principle if we were doing it from the side view and this was y. So we'll just work with the x coordinates for now. If this length is x and we have this z value here, which is the distance from here to here. Well, you know what? I think I'll start another diagram to try to simplify this a bit so it doesn't get all jumbled up. Okay, so I just drew half of the field of view from top view, and I put the theta here, this angle, to be equal to field of view divided by 2, so I don't have to write out a whole bunch of stuff. And we got this near distance here to the near plane, and this far distance here to the far plane. So this will be where we want to project our coordinates onto, like so, to get this coordinate. So as I was saying, we can say that tan of theta is equal to opposite, which is right here, divided by adjacent. In this case, we don't know opposite, so to find that, we can multiply this side and this side by this number here. And that will give us opposite is equal to tangent of theta times adjacent. And adjacent in this case is n. So we can write that as opposite is equal to tangent theta times near times n, the near plane distance. If we have this point here, for example, and we know its x value, assuming that we're looking at this from the top view, we can say that we have a triangle like this. So what we need is this horizontal distance to get the new x value. And instead of calling it x to avoid confusion, I'm going to call it h for horizontal. So we also have this depth value, z. We're not going to worry about y for now, but the same principles apply for doing it with y. You'll notice that h is to n as x is to z. And you can see plainly that these are similar triangles. So we can write those two relationships. So as I said, h is to n, or h divided by n, will be equal to x divided by z by similar triangles. So if we cross multiply, that gives us h times z is equal to n times x, and we need to isolate for what is h, because we want to know this x coordinate here, this h coordinate. So then that will give us h is equal to nx divided by z. Or if we wanted, we could say nu x is equal to n times x over z. You'll notice though, like if this value here is 1, then you just get x divided by z. So really what we're doing is we're basically dividing the horizontal distance and the vertical distance y to the point from the origin or the center of the screen, however you want to say it, and we're dividing it up based on the depth. We're making it smaller based on how far away it is. The further the z value, the smaller it is because you're dividing by a bigger number. And we're multiplying it by n, so we're getting the correct proportion here. And like I said, we can do the same for y. This x would be a y instead, a y here, y here. So the new y would be new y equals ny divided by z. Now, there's one difference though between the y and the x, because sometimes our screen proportions can vary. We use what's called an aspect ratio to multiply against the new x coordinate, this distance here, to get the correct proportions. So for example, if I had a screen that's shaped like this, or I had a screen that was shaped like this, if I had this square and I projected it to one or the other, the results would not be the same. We want this square to be a perfect square in both those views. So if I project the square normally, I might end up with something like this based on the width and height. However, if I multiply it by an aspect ratio, it can correct this horizontal distance and give us the square that we expect. So that way, whatever's on our image, it's going to look correct no matter what kind of screen resolution we're using, no matter what the proportions are. So if you look up here, I typed in aspect ratio is equal to height divided by width. And as you can see here, I corrected the x value, or the h value that it originally was, by timesing it by that aspect ratio. What we'd like to do also is normalize the z values for the device. So what we'll need to do, I'll just erase some of this first. Essentially what we're after is we want to know what percentage distance this is away from this near plane here. And to do that, first of all, we have to know the distance between near and far, which we'll call d, which I'll say is equal to far minus near. And this distance here, that would be the z minus the near plane. That's that distance. So what percentage is this z minus n relative to this f minus n? If we said 1 over f minus n, we can use that as a multiplier against the z minus n. And essentially what we end up with is z minus n over d, because this is times 1 over d, and we know that d is f minus n. So if this is 1,000 and this is 100 and this is say 600 or something, I'm not sure what value this is, but it looks like it would be around 0.65. So it's in that 0 to 1 normalized coordinates for the device. So what we need is a matrix that can get us that new projected position in x and y, and also normalize the z value. And we can do that from those equations that we already figured out. So figuring out how to get this as a matrix, remember before we figured out that this d would be equal to n, which is this near distance, times tangent of theta divided by 2, theta being the angle for the field of view. Now for this h, what I'd actually like to do is make it so that this is going to be a distance of -1, so that this is kind of normalized between -1 to +1 along x. So keeping that in mind, instead of saying h, because I don't really want to confuse it, I'm just going to call this x prime. So I'll just scribble that out for now. And what I want x prime to be is, well, let's see here. We know we want that length to be like it was 1, and we have some other distance down here. So I'm going to say that this will be, the other distance will be x prime, and we don't know that. So that's going to be equal to our opposite value, which is this d here, over our near distance. So those will be proportional. D is to n, this is n here, this is d here. D is to n as 1 is to x prime. If we cross multiply these, we get n is equal to x prime d, and then we know that x prime is going to be equal to n over d. We can substitute the 1 over d with what we had before for calculating this d, and what we'll end up with is n over n times tan theta over 2. So I'm just going to erase this and write it in more neatly. But anyway, the n's will cancel out, and that'll be 1 over tan theta divided by 2. So x prime becomes 1 over tan theta divided by 2, which is pretty simple, and it would be the same thing for the y, so y would be the same. However, what do we need to multiply against this to get it proportionally accurate? That aspect ratio from before. So effectively that tan theta divided by 2 is this. So what we can do is we can multiply the aspect ratio against it ahead of time and end up with the aspect ratio on the bottom here. So it's 1 over aspect ratio times tan theta over 2. As far as taking this logic, like I know how to make this all work if I were to just make a regular rasterizer and not use matrices. But as far as putting it into a matrix goes, there's probably other tutorials out there that explain it better than I could. It's actually really tricky to explain and a little bit time consuming. So I'm just going to show you the final matrix that is going to be created. There's an OpenGL version and a DirectX version. Okay, so we got the matrix here. So what you'll notice is we're scaling our y by this 1 over tan a, which we had figured out. And the same with the x, except we're factoring in that aspect ratio. And then for the z, there's some kind of tricky stuff that has to go on here involving homogeneous coordinates and dividing by z to normalize our z value. And we want this 1 here. So how exactly it's doing the same thing in the matrix, I'm not entirely sure. I'd probably have to multiply it all out and to check to see exactly what it's doing. But you want to make sure you got a 1 here and a 0 here. And for the DirectX version, or the way you normally do it in DirectX, these two would be swapped. And you're not going -1 to +1, so you could probably change this to just 1 instead of 2. And I believe this right here works out to z, or I should say far, over far minus near, which is kind of how we were doing it before. And that would go here for the DirectX version, if I'm not mistaken. So if you know more about this, feel free to add something to the comments. So I mentioned dot products before, which are good for figuring out how similar two unit vectors are in the direction that they point. If they're very similar, they'll be 1. If they're 90 degrees, they'll be 0. If it's pointing the opposite way of the polygon, for example, if we're dealing with polygons, then it'll be a negative number, in which case it would be backface colored, or it would be really dark. So I already talked about that. I'll just briefly mention cross products because they'll come in handy if you start getting into 3D stuff. And we might dabble in the 3D a little bit in this upcoming batch tutorial that I'm going to make. The cross product, I'll just write it out real quick what it's actually doing. So what this crazy little cross product method does is it is used to determine the 90-degree angle vector between two other vectors. So let's say I have a plane here, or a polygon, and I have these two vectors. From this, I can compute the 90-degree or perpendicular vector to these two vectors. And that way I can get the surface normal of a polygon. And you just want to make sure to normalize it so it's a length of 1 if you're going to add it to your normals. And I could do that for any two vectors. I could figure out this vector that's perpendicular to both. So if you want to recompute the normals of polygons that you've loaded, or you might even just want a 90-degree angle to two different directions, maybe to have a character strafe sideways or something. Actually, for that, I'd probably just use one of the sideways vectors for the camera matrix, which I kind of covered that in my 3D character tutorial. I think I'm going to make that it for this tutorial for now, and the next time we'll work on making a batch renderer, and maybe we'll make a little video game that takes advantage of it, and set up a 2D camera and a 3D camera, and try playing with having a game work with both. Maybe even do a little bit of 3D manipulation within the 2D realm. Thank you for watching.